So we've looked at vapor pressure and boiling point of a solution versus a pure solvent. Two other properties we're going to look at. This one, next one is melting point, MP. And unfortunately, I don't have a good mechanism to explain this for Chem 51, but I have something that you may know of or at least have heard of. So when I lived in Tahoe, they would commonly apply salt to snowy, icy and snowy roads. So think about this. Say I've got air at -2 degrees C. And I've got a roadway. And on top of that, I've got snow and ice. Well, we know that the melting point of ice is 0 degrees C. So 0 degrees C, the air is colder, the melting point is higher, it isn't going to melt. But imagine this. If over here, I'll extend the road, and I'll extend the layer of snow and ice. But over here, I start putting salt. And there's always a little bit of water, so I start getting a little bit of dissolving going on there. So now I've got pure snow and ice, and over here now I've got snow and ice that's becoming a solution as the salt sort of dissolves into the snow and ice. So over here, I start to get a solution. I'll say this: snow, ice, salt, solution. Now think about that. The air is -2. This melts at 0. Well, the air is lower than that. What do you suspect that the melting point of this solution is going to be? Why would we put this on here and turn this into a solution? We're trying to get it to melt, right? So somehow we must be lowering that melting point. And in fact, now over here at my solution, the melting point is -4 degrees C. Now it's lower than the air temperature. Or another way to say it is, the air temperature is higher than the melting point of this solution, and we get melting. So I'm not going to go through the mechanism of that, but at least you've heard of this, putting salt on the roads. So we'd say, well, it lowers. Why is salt applied to snowy roads? To melt it. And to melt it at a lower temperature. Okay. So there's melting point is dropped. Now, this last idea is osmosis or osmotic pressure. I'm going to draw a couple pictures here again. Here's my container of some sort. Now what I'm going to do is I'm going to put a semi-permeable membrane in the middle there. Now, that's just a membrane that, if I'm going to draw this, that molecules can pass back and forth. So what I've got on one side is pure solvent. So this membrane allows the water molecules to move back and forth. I'll label this up here. Well, this is my semi-permeable membrane. Now I'm going to make one change here. Pure solvent on both sides. I'm going to turn one side into a solution. So now I've got pure solvent on one side, and I've got a solution on the other. I'm going to just say, so I had pure water, I sprinkled in some solute, allowed it to dissolve, and then wait seconds, minutes, hours, whatever. And what I notice is this. When I come back to this thing, that's what I observe. Well, similar to the way the solution has a lower vapor pressure, one way to think about this is a tiny bit of a fib, but it's not bad. The solute particles here block some of the flow going in this direction. So we'll say solute blocks or restricts some solvent. So effectively what we get is, it isn't sort of arrows like that. It's really, I've got an arrow like that and an arrow like that. Well, over time, if the solute particles are blocking this and we get that flow, over time we end up with this. And this is called osmosis. Sometimes we'll call it osmotic pressure. You can think of it in two ways. It's the pressure that forced that liquid up higher. So we go, oh, there's a higher pressure on this side than on this side because there's a higher height of liquid. Another way to think about it is the osmotic pressure is the pressure that is forcing the liquid to that direction. But at some point it equals out and we end up with that. Okay, so we covered vapor pressure, boiling point, melting point, and this idea of sorry, it's early in the morning. I have not had coffee yet. This idea of osmosis and osmotic pressure.